This video is going to cover section 5.2, verifying trigonometric identities, part of Unit 5, Analytic Trigonometry. This is actually one of my favorite topics, so I might get a little bit happier with this one, just FYI. We have a few guidelines you might want to copy because they do kind of help you out with where to start. Sometimes if you're not too familiar with identities, you can get a little bit flustered. Okay, so number one is to start with one side. You always do one side first, and then just kind of work it through and make it match the other side. Okay. Um, Usually, you want to go with the one that looks more difficult because that's the one you can probably break down to match the other side. Okay. Number two, try factoring, squaring, adding fractions, monomial denominators, etc. So in this case, for the adding fractions part, what I mean by that is if you have like two fractions, you can try adding those two together and see if that's going to help. Do not add extra things to it on the side because that could change the value. Okay, what we are allowed to do is multiply by a monomial denominator, which we'll see. I kind of didn't get to fit it there, but it goes right here, which we'll see in the last second to last or last example. Okay, number three, this is the big one. You need to use your identities. Yeah, we're going to substitute. In your foldable, you have here under tab number 2, folded. Under tab 2, you have the identities that we're going to be using for this one. You have your reciprocal identities here at the top, which are basically just the reciprocal flip. Your quotient identities, which are just the basic ones, tangent and cotangent being x and y, sine and cosine respectively. And you have your Pythagorean identities, which we use quite a bit of. I went ahead and added a few more. Right? And they're like super tiny, but I just put them here because I noticed in class that when we saw something like this, let's say you had 1 minus sine squared theta, you didn't really know what to do with it. And basically it's this identity, just moving this one over to that side. So if you want, you can copy them. You don't have to. We can always just manipulate this. Okay. And same thing with this one. I didn't copy the last one because it's kind of the same as this one, just with the different trig functions. But anyway, we're going to be using these identities quite a bit in this subunits. Okay, so go ahead and move that away. Let's go ahead and start with an example. As I mentioned, we do not I didn't mention that one, but we do not cross multiply. So if we have two equations, kind of like this one, we're not going to cross multiply because in this unit, we're trying to prove equality. And if we do that, we're actually going to be changing the values, okay? We're also not going to be adding or subtracting quantities to both sides. So we're not going to add something additional to both sides because that could change the value, okay? We're trying to prove equality, which means we work with one side, make it match the other. Let's begin. Example 1. We have verify secant squared theta minus 1 over secant squared theta is equal to sine squared theta. So right off the bat, I'm going to say that this one looks a little bit more difficult. Okay, so I'm going to work with the right side in this one. And I'm going to try to make it match sine squared theta. So what do I know about secant squared theta? Well, I know from my foldable that this one, the Pythagorean identities, has a secant squared theta there. So secant squared theta is equal to 1 plus tangent squared theta. Okay, and I also put some little notes here that if I have it like this, secant squared theta minus 1, so basically if you move this one right here, if you move it over to the other side, that's equal to tangent squared theta, okay? So I can replace this top part right here with tangent squared theta, okay? And that's the first thing I'm gonna do. So there's that, and I'm just gonna copy everything else. I'm only gonna work with the left side, and I'll bring this one down at the way in because we're trying to prove that this is equal to that. Okay, so how is that going to help me? Well, not much yet, but I also know that tangent is equal to cosine, sine over cosine. So from here, we know that tangent of theta is equal to sine over cosine. Okay, and I also know that secant theta is 1 over cosine theta. Now I know that they're both squared. That doesn't really make, I mean, all it's going to do is I can put a square on all of these. It's the same thing. Okay, so we're going to use this and see if that'll maybe help me simplify to sine squared theta. Okay, so I'm going to plug tangent squared theta with this right here. So that will be sine squared theta divided by cosine squared theta. That's the top part all over. This one I'm going to replace with 1 over cosine squared theta. And why am I replacing with 1 over cosine? Well, because this has to equal sine squared theta at some point. So since this one has a cosine, I should probably try to get rid of the cosine somehow. So let's see, 1 over cosine squared theta. Okay, and you can see here that we have what we have. So we're looking at this part right now. Okay, that's the fraction, a fraction within a fraction. We have a double fraction, so we're going to have to do our keep flip change, right, for this part right here. So that will look like the following. Sine squared theta, so the top fraction over cosine squared theta, times, I'm going to flip this one, so cosine squared theta over 1, and look what happens. So these are gone, and we're left with just sine squared theta over 1, which is what I was trying to prove way up here. And we have proved equality, meaning that this original, this is equal to this, using identities. I'll go ahead and zoom out to the whole problem. Well, kind of the whole problem. All right, let's try another one. Super fun. These are fun, I hope. Example 2. We have to verify that sine squared theta plus cosine squared theta over cosine squared theta times secant squared theta is equal to 1. So just like the other one, it looks like the left side is the more difficult side. And right away, I see this Pythagorean theorem thing going on here. I'm going to use this identity right here. This is equal to 1. So I can replace all of this with 1. It does benefit to memorize the identities when you're dealing with these kind of problems. Personally, I have, the main ones memorized. This one's an easy one to remember. But some of the other ones are a little bit not, they're not as easy. So it's okay. You'll get there. For the other two, I don't really know too much. I do know that, let me see. Well, I know that cosine is the reciprocal of secant and vice versa. Yeah, so what if let's try replacing one of them. I'm going to replace secant just because, I don't know, I'm just going to replace secant squared. So we're going to be left with 1 over cosine squared theta, okay? Now I'm going to replace secant square with 1 over cosine squared theta. Remember that secant square, this is just the reciprocal of this one, so I just have to flip it like this. And again, this is part of your reciprocal identities, which is at the top, okay? So secant is 1 over cosine, and if it's squared, like so, well, you just got to square cosine also, okay? So then here, where I have the secant squared theta, I'm going to have 1 over cosine squared theta equal to, the 1. And at this point, hopefully you can see right away what's going to happen if we put this over 1, because that you're allowed to do. You're not changing the value. It's just saying this is divided by 1 is the same value. You can see that if we multiply these two, okay, we're going to end up with, so let me rewrite this, 1 over, okay, we're going to have cosine squared theta times 1, which is cosine squared theta, over 1 times cosine squared theta, which is also cosine squared theta, which is 1. 1 divided by 1 is 1. And I have proved once again equality. Yay. Okay. Another thing you could have done at this point, I mean, and I've shown you this before, is if you're multiplying a fraction times another fraction, if you have something that's on the top and something that's on the bottom, you can kind of just do that, which would have given us the 1 over 1 right away. Okay, because you're just dividing, so this gets divided by this, and you get that one number that we're looking for. That is it for that example. Here's the whole problem. Well, actually, I can't get this one. So hopefully there's the top and there's the bottom. Okay, next one. Okay, we're already on example 3. Isn't that going by really fast? And isn't it super fun? All right, so example 3 has a different angle notation, but don't freak out, it's still an angle. We have verify 2 cosecant square beta. Okay, this is beta. It's just another Greek letter. It's still an angle, so don't freak out about it. Is equal to 1 over 1 minus cosine beta plus 1 over 1 plus cosine beta. So this is kind of what I was talking about when it said adding fractions, okay? We're going to try to work with the right side this time because I see that there's 2 fractions and I can probably try to add them. Yeah, I'm going to add them up. Oh, sorry. Add them up and see if this will give me this over here, okay? So when we're adding fractions, we can use the 2 fractions. We can use our butterfly trick, which is basically going to be the following. 1 times all of this. I'm going to write this one a little bit smaller because I don't have too much space. So 1 times 1 plus cosine beta, like a slanted B, okay, plus these two. So 1 times 1 minus cosine beta all over, you multiply these two. Okay, so that's going to be 1 minus cosine beta times 1 plus cosine beta. And I haven't actually multiplied anything just yet. I'm going to do that in the next step. I'm just kind of showing you the setup. These two multiplied, they're up here. The bottom two multiplied, they're down here. This is a common denominator, okay? So on the next part, we're going to simplify all this. So if I distribute my 1 to both of these, I get 1 plus cosine beta plus 1 minus cosine beta, okay, all over, here we're going to FOIL. And we did something like this in class, so let's see if you can follow, okay. 1 times 1 is 1. If I multiply these two, so I do the inside and the outside, we get negative cosine beta for this part, and 1 times positive is going to be positive cosine beta, which is going to give us 0. So there's no middle term, okay? Last but not least, we do the last term. So negative cosine beta times positive cosine beta is negative cosine square beta. Remember that beta is just an angle, so don't let that throw you off, okay? From there, I can see, that's a plus, by the way. I can kind of see that my cosines on the top are going to come out to a 0. So let's write out what we have. We have 1 plus 1 is 2 over 1 minus cosine square beta. And hopefully you can see what's going to happen next, okay? We want it to be 2 cosecant square beta. So cosecant is 1 over sine, which means if I can get this to be a sine, I can probably work that out, okay? And luckily for us, this is in fact equal to sine square beta. Why? Because if we look at our foldable again, okay, we have from this identity here, either the first one, if you were to move cosine squared theta to the right side, we get sine squared theta is equal to 1 minus cosine squared theta, which is what I have right here. Okay, so this is equal to 2 over sine square beta. Of course, we're saying beta in this one, not theta. And we're almost done. We also know that sine square of an angle is the same as our reciprocal function, 1 over cosecant square. That's one of our reciprocal identities. Okay, so this is equal to 2. Ooh, I'm almost out of space here. 2 over 1 over cosecant square beta. Ignore this problem for now, which means that if I go ahead and do my key flip change, I get 2 times cosecant square beta over 1, which is just 2 cosecant square beta. And this is what I wanted up here. So we are done. Okay. All right, next one. We're almost done. We have 2 more examples. We have another identity, secant square x minus 1. Secant square x minus 1 is equal to a negative sine. Oh, I'm sorry. Sine x squared minus 1 is equal to negative sine square x. So in this one, I'm definitely going to work with this one. I'm going to multiply these two and see what happens. Okay, so let us do that. We can go ahead and do the first terms. So that's going to be secant square of x times sine square of x. And I really can't, I mean, you just got to put them next to each other at this point because it's a different function, right? And then we're going to have the outside. So secant square x minus 1 is going to be minus secant square x. The inside, so minus sine square x. And the last, negative 1 times negative 1 is positive 1. Okay, so how is this going to help me out? Let's see. I can probably pair some things off together here. So let's do that. Let's try that. Let me see. How is that going to work? If I put my, actually, this might not be the route to go. Okay, so if this happens, and this kind of, actually, I forgot to show you that part. Let me go back really quickly. I did this on purpose. One more thing on this one. We'll go back to that problem. If all else fails, okay, replace with sine and cosine where applicable. Always try something. So if you try something and it doesn't work, try something else. We can try something else. So I think that's what's going to happen with this one because I don't see anything that I can really do with these. I mean, I can change them to sines and cosines, I guess. I can do 1 over cosine. I mean, yeah, let's try it. Why not? Let's try it. So this secant square x is the same as 1 over cosine square of x, okay? And then sine square of x just goes next to it, okay? Minus, again, this is going to be 1 over cosine square of x minus sine square of x plus 1 is equal to whatever. Right here, I can see that if I put these together, so this part right here, I can probably put them together like this. And what do you know? We have tangents. So let's replace this with tangents. So tangent square of x, okay, minus, what else do we have here? 1 over cosine square, well, that's not really going to help us. Let's change it back to a secant square x. Okay, so I'm going backwards. I'm going back to this, okay? And I actually do know the other way to do this, but I want to see if we can work our way through this because, sometimes there's more than one way to do something. So minus sine square of x plus 1. Okay, I know that these two are related somehow. I know that if I look at my identities, okay, you see how we have 1 plus tangent square theta is equal to secant square theta. So we can probably do something here. We can probably replace something. I think I'm going to try this one. So tangent square theta is equal to secant square theta minus 1. I'm going to try that. I'm going to replace this one with secant squared theta minus 1. Why am I going to do that? Because I see that it has a minus 1 and there's a plus 1 over here. So that will get rid of that for me. Yeah. Oh, actually, this is going to work perfectly. Okay, so we're going to replace this with this, which is going to give us secant squared theta minus 1. So that's this substitution. Okay. Minus, I'm just copying everything else. Minus secant square. When did I turn these into thetas? Oh, this is an x. My bad. This is an x. Okay, x. X and x. Minus sine square x plus 1. Okay, now check this out. We have minus 1 plus 1. We have secant square x minus secant square x. And what is left over? Negative sine square x, which is what we wanted. Isn't it amazing how even if you start up a little bit wrong, you can still rework this and get this. So my original way to solve this was actually another route. But since I went ahead and did this, we try something else. And if that does happen to you, try something. Try substituting with another identity. And eventually, if you're plugging in the right identities, you will get there. Okay. So persevere. Always push on. Okay. Last example. That was fun. We're going to do this one up here. This one is a little bit different because this is the one where you will have to multiply times a monomial denominator. Okay, I'm going to show you what that means. It sounds more complicated than it actually is. So for this one, we're going to work with the right side. Okay, if you notice, there is no identity for 1 minus cosine x. There's one for 1 minus cosine square x, but this is not squared. You can't just put a square. Like, that's not going to fly. So what we're going to try is we're going to multiply this by a monomial denominator. What that means is I'm going to take something and multiply it on the top and on the bottom, which I'm allowed to do because this is technically just equal to 1. Remember, anything divided by itself is equal to 1. And if you multiply anything times 1, you're not changing the value, okay? When you have a problem like this, you typically want to do kind of like the conjugate of this. So if you kind of go back to your complex numbers, it'd be like saying 1 plus cosine of x. 1 plus cosine of x. So just change the sign. And that will work sometimes, okay? Sometimes you just got to kind of play with it and see what works. All right, so we're going to multiply this times this and this times this. See what happens. So if I multiply the numerator by all of this, basically you have to distribute, right? So you would have sine of x, because sine of x times 1 is still sine of x, plus sine of x times cosine of x. So now these two are right next to each other. On the bottom, we have a FOIL. And it's kind of like the one before, not the one before, two before, where you multiply. So we get 1 times 1 is 1. The middle terms are going to not cancel out. They're going to give us a 0 because we get negative cosine, and then we get positive cosine of x, which just gives us 0. Okay, so there's no middle term. And then we do cosine of x times cosine of x. One of them is negative, so it's minus cosine squared. I keep putting theta. Minus cosine squared x. And this is an identity. This is equal to sine square of x. So we're going to rewrite this again. Sine of x plus sine of x times cosine of x all over sine square of x. So from here, I went ahead and rewrote it with the identity sine square x, which is one of your Pythagorean identities. Okay. From here, you can notice that there's signs everywhere, right? But excuse me. If we look at what we're trying to match, you have two terms. You have cosecant x and cotangent x. So I have to somehow get two terms out of this fraction. So what am I going to do? Well, I'm going to break it apart. I'm going to put this over this. So sine x over sine square x plus, okay, this one, sine of x cosine x plus, I'm sorry, over sine square x. Are we allowed to do that? Yeah, we're allowed to do that. It's kind of like saying 1 plus 3 over 5. You can say this is the same as 1 over 5 plus 3 over 5. Yeah, same deal. Okay, so from here, you can see several things are happening. One of the signs is now gone. So we have 1 over sine x because one of them is now equal. It's kind of like turns into a 1, right? It gets canceled out. So it's 1 over sine x. Over here, same thing happens. This one goes away. One of them goes away on the bottom. So we're left with cosine of x over sine of x. And lo and behold, these guys are reciprocal identities. Okay, this one is 1 over sine is cosecant. So we have cosecant of x plus this one cosecant, cosine over sine is going to be, where is it? Right here, cotangent. So cotangent of x. And is that what we wanted? That is what we wanted. So we have proved that this one is in fact equal to each other. Another happy face with teeth this time. All right, the last one I'm just going to have you copy. We'll do this one in class. See, maybe, or you try it. Try and see if you can solve this one. This one is similar to this one. It's good practice, but we will go over it in class. If you have any questions, let me know.